Okay, next on we're going to have a look at circuit control, particularly when it comes to your distribution network and your customers out there. Now, if you cast your mind back to our early electrical theory, we looked at a basic circuit, and a basic circuit has to consist of a voltage, and it has to consist of a load, and the load here, we can call that your customer. That could be someone's house, or it could be a housing estate, or it could be the whole of Liverpool or Manchester or anything like that. But effectively that's your customer, and this is your supply of energy to your customer. And we know from our theory that we have to be able to control that supply using a switch. However, we also need what we call a protective device. I'll call it PD for short. And a protective device is another device which goes in the actual circuit, but it goes before the switch. And in this case I'll show it as a fuse, and here is our complete circuit coming back like that. Now we knew in our basic circuit we have to be able to control this current that's going through the circuit, which we can call I. So we've got VI, and we can call this is our load R, or sometimes it's called Z if you're doing level 3, but it's measured in ohms. So the amount of current flowing through this circuit depends on the resistance of the load. As the resistance of the load goes down, the current goes up. So as people switch more and more things on in their house or on their housing estate, the current being delivered to that house or to that estate goes up. And of course we know what happens when the current goes up. These cables that are supplying the customer can get warm, and we can lose energy in those cables and elsewhere in the network. Okay, so that's our basic circuit that we looked at last time. However, in your network we need to be, because we're working on low and high voltages, but they're nevertheless dangerous voltages as far as you're concerned, we have to have a way of isolating the circuit, and that's done with this symbol here, which is an isolator, and then we have a protective device which is a circuit breaker, and then we have a switch which is shown like that, and there is our load or our customer. So there is VS, there is the current, there is the load, and you've got 1, 2 and 3. Now an isolator is a form of mechanical switch, but it's designed to be operated under no load. That's very important. It has to be operated under no load, because these things are not really designed to control the circuit. The switch is designed to control the circuit, and the switch is very often an oil or a gas circuit breaker, which is designed to switch on and off at fairly regular intervals. Because when you switch on and off the circuit, you'll get a lot of arcing across the contacts, which will deteriorate the contacts. And in an isolator, if you use that to switch it on and off regularly, it would damage the the isolator. So you only use a switch that's specifically designed for that. So that's a symbol for a switch. And this is our protective device. It's a circuit breaker. Now, a circuit breaker is an automatic type of switch, which if too much current goes through it, it automatically operates like a circuit breaker does in your household consumer unit. But you can see here that if you wanted to work on the protective device, or you wanted to work on the switch as a fitter, then you would need to isolate the supply using this switch here. And this is very often what we call locked off. Literally with usually a couple of padlocks which keep it locked off for safety reasons when you're working on the rest of this circuit. Alright. One of the other types of protective device that can be found in this part of the circuit is a fuse. And the symbol for a fuse is simply a rectangle like that with a wire going through it. And the fuse always has a rating, for example 100 amps. And that's the rated value. And what that means is that this will operate continuously with a maximum current of 100 amps. If it goes over 100 amps, then it may get, well, it'll probably start to get warm, and as it goes up and up and up the current, it will start to get very hot, and eventually it will melt. If the current goes up very, very rapidly, then it will what we call blow very quickly. So this short piece of fuse wire inside the fuse will actually melt very quickly and blow very quickly. Most fuses have what we call a fusing factor, and it can vary depending on the type of fuse and the manufacturer of the fuse. It can vary between, say, 1.2 to 1.5. In other words, this fuse will not actually blow. If it had a fusing factor of 1.2, it wouldn't blow until about 120 amps. But it's designed to be continually operated up to 100 amps. So that's what we call its rating, not to be confused with fusing factor. Because sometimes you get asked questions about fusing factor and sometimes about rated currents as well. Another thing you need to remember is what we call discrimination, and here we might have fuses effectively in series. So for example, this fuse, and this is your link, your consumer unit, that could be a 100 amp fuse. This could be, say, a 32 amp fuse, and that might be feeding a fuse that might be, say, a 13 amp fuse inside, effectively inside a plug top, which is controlling a portable appliance. So in your circuit you have effectively 3 fuses connected in series. So that's live, that's neutral. Sorry, I'll take that link out there, forget that. So that's live and neutral. There's our circuit effectively. I could put the, I'll show your, there's your load in there, for example. Could be an immersion heater or something like that. How are we doing for time? And discrimination means that the smallest fuse closest to the fault has to blow first.